linkage. And gene linkage is really an exception. We don't have to take into account gene linkage most of the time because most genes are not linked together. Most of them will follow the two laws that Mendel said, the law of independent assortment and the law of segregation. They will all follow the law of segregation, but most will also follow the law of independent assortment. But gene linkage becomes important because it's a way for us to map chromosomes. And it's a great research tool. It allows us to find genes when we couldn't normally find them. So let's take a look at a gamete stem cell. A gamete stem cell going to go on to make gametes. Could be sperm, could be egg. They'll go through meiosis. We'll review that later on next week. But a gamete stem cell has a typical number of chromosomes in it. So there are 2 copies of each chromosome. Well, let's take a look at the two random chromosomes in a gamete stem cell. The first one we'll say is a maternal copy of chromosome number 4. And on chromosome number 4, there's gene A. And close to it is gene B. Now, there are other chromosomes in this organism, so let's take a look at, let's say, chromosome number 7. The 7 is a little bit bigger, and it has gene C and gene D. So what did we say this was? We'll call it 4 if we didn't before. We'll call this 7. And they're green because they were inherited from this organism's maternal side or mother. Now, they've got 2 copies of each of those. This one came from mom, so the next one, the other copy would have come from dad. So we'll make it look the same. And over here, we've got gene A. And over here, we've got gene B. And down here, we've got a copy of chromosome 7 with C and D. So this is 7 from dad, 4 from dad. And so we can see that each of these stem cell has 2 copies of each chromosome. So these are our 2. These are what we refer to as homologous chromosomes. And those homologous chromosomes are, one came from mom, one came from dad. They have the same genes in the same place or in the same order. And that means as far as gene linkage goes, we've got 3 possible situations. The first situation, the genes that you're talking about are on different chromosomes. So A and B are on different chromosomes from C and D. If you were on a different chromosome, there's no linkage. You're not on the same structure. You're going to follow the law of independent assortment. You're going to follow the law of segregation. They're not on the same structure. They can't be linked together. The second one is what we see over here. These genes are far apart on the same chromosome. Again, there's no linkage. But the reason there's no linkage is not because they're on completely different structures. It's because of crossing over. Crossing over is very likely to occur between C and D. So they're going to act like they're not on the same structure. They're going to be just normal genes that follow the law of independent assortment and the law of segregation. But up here on chromosome number 4, we have two genes close together on the same chromosome. That means they're very likely to be inherited together. So if you get the green A, you're probably going to get the green B. If you get the red A, you're probably also going to get the red B. Because when that stem cell goes to make gametes, there's a less likely chance that there will be crossing over here. Much more likely to happen down here between these two. So these two, when you make a gamete, that gamete is probably going to have a green A and a green B. The other gametes are going to have red A's and red B's. Occasionally, there will be a crossover event between A and B. And how often that happens allows people to make maps of chromosomes. That's how we know that A and B are close together on chromosome number 4, and that C and D are further apart on chromosome number 7, and that A and B are on 4 and C and D are on 7. We can use this crossover event between linked genes to figure out what genes are on what chromosome. So it's a very good research tool. It's a very good genetics tool. It looks like it violates the law of independent assortment. It really doesn't. It just means that crossing over doesn't happen as quickly there or as often there as it does in other cases. The other thing in this section that was important was polyploidy. And polyploidy means having three or more copies of each chromosome. So instead of having 2 copies of number 1, you would have 3 copies of number 1 in the cell. Sometimes even more than that. This works okay in plants, many plants. In fact, when plants have extra copies of chromosomes, they are super plants. That's how we get giant strawberries. It's also how we get seedless watermelons. It makes them so they can't reproduce. We have to have ways to make the initial plant, but those plants are bigger, stronger, and grow better. It can also happen in a few animals. I mentioned goldfish and worms, but in most animals, polyploidy is not going to work. But in agriculture, if you are growing things like strawberries and watermelons, it's a very useful tool. All right, I'm going to just wrap that up there. And next week you can plan on, or next time you get a message from me, video from me, plan on trying to tie all these things together. And then we'll do a little review video, and I'll put a review assignment up. And then following that, I think we're going to head back to energy in organisms so that we can begin talking about ways that organisms interact with one another. Stay safe. Send me questions. Always glad to hear from you.